Okay, so section 7.5 is a little bit different from what we've worked on before because it involves a lot of physics formulas that we're going to sort of, no pun intended, integrate into our calculus problems, right? So we're going to start off with the definition of work, which, if you've taken physics, work, it, there's a couple of different definitions for work here. If we're talking about work done by a constant force, then that's going to be if an object is moved a distance d in the direction of some applied constant force F, then the work can be calculated by using this formula: W is equal to F times D, right? Where F is that constant force and D is distance, or sometimes it's called displacement. Okay. So the first example that sort of the book opens up with is determine the work done in lifting a 50-pound object 4 feet, right? So I kind of drew this little diagram here where we have this box that's 50 pounds, and we're just lifting that 4 feet in the air. So our y-axis here just represents that feet or the height, or you could think of it as the distance or displacement. Okay. But just applying this work formula, if we have constant force, then it's there's really no calculus involved. W is equal to F times D, and that's just going to be the force that was given, 50 pounds, times the 4 feet. And that's going to give us something, 200, right? I don't have my calculator on me. I'm pretty sure it's just 200. Okay. 200. And if you're not familiar with like measurements in different kinds of units, again, you may have seen some different kinds of units in a chemistry class or maybe a physics class already. Then what we're going to get in terms of our units for work in this case is going to be something called foot pounds. Okay. So you can think of that as just literally feet times pounds. And that's it. That is the work that's required to move that object up 4 feet. Any questions, comments there? That seemed like super easy, right? But then obviously there's some things that we need to consider. First of which is going to be there's a bunch of different systems of measurements. Again, if you've taken different science classes, which I don't know where you guys are in your math or your engineering education, but you should kind of be familiar that there are these different systems of measurements, like the US, sometimes it's called US standard measurements, international system of measurements. But if we're talking about work in the US system of measurements, we're going to be using foot pound. That's going to be the units for work, which means that our force is going to be in pounds and distance is going to be in feet. Okay, so if you multiply these two together, you get foot pound. Okay. In international units, the units for distance is meter, and the unit for force is something called newtons. And so if you multiply newtons together with meters, you could get something called Newton meters, but usually that's just called joules. Okay. And then there's another system that you might run into in some of these problems called the CGS system, which stands for centimeter gram second. Um, because a Newton is kind of large and a meter is kind of a long uh, distance. So if you kind of wanted to minimize that distance, you could measure in terms of centimeters, in which case force would be measured in something called dynes, and then you would get this erg measurement for work. Okay. But I would say that most of the time we're probably going to use these two systems of measurements. Okay. And then if you ever needed to convert between those two systems, I put just a couple of conversion factors here that 1 foot-pound is approximately equal to 1.35582 joules and 1 Newton. is approximately equal to 0.22481 pounds. Okay. So like if you wanted to, for funsies, you could go home, weigh yourself in pounds on a scale, and then you can convert that into newtons. But if you never thought of it before, weight is mass times acceleration, or force is mass times acceleration. So force is equal to mass times acceleration, right? There's a very um, common formula used in physics. And so if you think about your mass times the acceleration due to gravity, that's what gives you your measurement of weight. Okay, so mass and weight are not the same thing. Just some little fun facts, I guess, that you need to be aware of, or hopefully you are aware of. If you weren't then, now you are. But now we can get into some of our tricky formulations, right? So now getting into the calculus of it. Work done by a variable force is going to be given by this formula, which essentially um, you can think of it as delta Wi, which you can think of this as incremental work. And what I mean by incremental work is that typically in calculus, what you're doing is you're taking some function and then you're breaking that function up into a bunch of different pieces. We call that a partition, right? And so this symbol delta in this case of our definition means that partition, right? That you've taken the function and you split it up into infinitely many little subsections, right? So as the distance, as the norm of those subsections gets smaller and smaller, right? As those rectangles get thinner, then if we take the sum of all of those increments of work, then that's the same thing as the limit as those subsections get smaller of the force function times some incremental distance, right? Where delta x means that really, really tiny distance, incremental. Okay. And whenever we take that limit as n goes to infinity, or as the partitions get smaller and smaller and they approach zero, then we end up spitting out this integral. Okay, so this is essentially the same thing as force times distance, right? We're going to have some force function that's going to vary with respect to x. Sometimes it'll vary with respect to y. And then we'll have dx, which represents that infinitesimal distance. Okay, so this is the analog for that constant force or constant work definition. Okay, so whenever we have a force function, then we have to sort of throw that into our integral and integrate it, because it's not just going to be as easy as multiplying two numbers together. Okay, so in some of the examples we're going to look at, we're going to utilize some of these well-known force laws from physics, like Hooke's law. Hooke's law describes the physics of a spring. So usually when I draw a spring, I always make a little block, and then I just do these loop-de-loops indicating the spring. And I will indicate some sort of force with an arrow, because usually you're compressing that spring, right? So Hooke's law says that the force um, is going to be equal to some constant, usually called the spring constant, times the displacement of the spring within its sort of normal elastic range. Okay. Uh, Universal law of gravitation, Newton's law of gravity, is given by this formula where the force of gravity is equal to a gravitational constant, usually measured in meters cubed per kilogram second squared. We don't really need to know this gravitational constant. I mean, this is the gravitational constant for Earth. But what you have in this formula is basically a constant times the two masses of the objects that you're talking about divided by their distance squared. Okay. So we can use this to calculate force if we needed to for a particular problem, or we'll use that as our function of force, where the distance might be measured in terms of x, right? So that would be a function of x. And then Coulomb's law describes basically the electromagnetic attraction between two charged particles. So this formula, if you've never sort of encountered it before, You would see it in physics too, because that's when you talk more about electricity and electromagnetism. This is analogous to Newton's law of gravitation, right? Because you have some constant out here, you're multiplying the charges of these two particles and then dividing by the distance squared, that distance between the two particles. Okay, so even though these look a little bit different, they are pretty much the exact same formula. So if we ever have to use Coulomb's law to like work on a problem, then we have this function. Again, the distance might be represented by x or y, depending on how we're going to orient those particles in space. Okay. All right. So that's a lot kind of being thrown at you, and the textbook is just like, oh yeah, you should know these things, right? But now we're going to put them in action with some of these examples. Okay. So the first example says a force of 30 newtons compresses a spring 0.3 meters from its natural length of 1 meter. Sorry, 1.5 meters. Find the work done in compressing the spring an additional 0.3 meters. Okay. So I always think that it's a good idea to draw, well, in the past we've just drawn the function, but now we kind of have a physical system that we need to sort of represent with a picture. So I'm going to say my first step is to draw a picture. And like I said, I usually draw a spring as a little block and then some loop-de-loops here. Here's my spring. And I'm going to put this as state 0. The unaltered spring has this length of 1.5, right? Where there's no force applied. But then the problem states we're going to take that spring and compress it, right? So there is going to be a force that's applied here. And it says that this force is equal to 30 newtons. Okay. And if this spring is sort of contracted or compressed from 1.5 meters, but it's been compressed 0.3 meters from its natural length, what is the length of the spring now? How would we find that? Just think about holding a slinky in your hand, right? If it's a length of 1.5 meters and then you compress it by 0.3 meters, how do you find the new length? Subtract it. Yeah. So I saw you guys flipping through the notes and I was like, okay, you guys think that this is a trick question and it's not. So we just need to subtract it. So like the new length of the compressed spring should just be the 1.5 minus the 0.3, right? So 1.2. So here, this compression was 0.3 meters. You guys okay with that? Okay. So once we kind of have that situated, just kind of a picture in our head of what's going on, we need to talk more about this force here because we know that we're looking for some force and we need that to be a function of x so that we can integrate it, right? But right now we know that that's equal to 30 newtons, right? However, we know this x value because if we sort of go back to our definition of Hooke's law, Hooke's law says that force is a function of this distance, right? That distance of compression. So we could represent this as F of 0.3 is equal to 30 n, right? Where 0.3 is our x value. Okay. So by Hooke's law, we know that the force is equal to some spring constant times the distance, and I'm going to use that distance and represent it by the variable x. Okay. And this might seem a little bit convoluted, but we have the force of 30 newtons. That's equal to some constant that we don't know times a compression distance, which we do know to be 0.3 meters. So this second step that we're sort of hinting at or like sort of approaching is that we need to find the spring constant so that we can sort of put our entire function together so we know what f of x is, right? Like f of x is not going to be this constant value all the time. It's only 30 newtons when the distance here is 0.3. But since this is just a simple multiplication relationship, we can solve for k by dividing that 0.3 over to the other side of the equation. So if these cancel out, we'll get k is equal to whatever 30 divided by 0.3 is. Okay. So 30 divided by 0.3 is 100. So that is our spring constant. Kind of some preparation that we have to do here at the beginning. Okay. Any questions about what we've done here so far? Zoom out. So now let's talk about this variable work, right? So we have work, which is what we're trying to find. And we know that's going to be the integral from a to b of our function f of x dx, right? Because it's just force times the distance, okay? But this f of x that we found, now that we have the spring constant, is just going to be that spring constant times x. So the integral that we're really looking at is of the function 100x dx. Okay, and maybe over here I should say the completed function f of x is equal to 100, that spring constant, times the distance x. In case that wasn't clear. But now we just need to find the limits of integration. So like, let's read through the problem again. It says we need to find the work done in compressing the spring an additional 0.3 meters. Okay. So in state one, we compress the spring with 30 newtons to a compression distance of 0.3. So that's going to be our starting point right there. And so if we want to get an additional 0.3 meters of compression, what would this upper limit of integration be? Or how would we find that? By adding that additional 0.3, right? So that's just 0.3 plus 0.3, which is going to be 0.6. Okay, so you need to watch out because some of these problems get a little tricky. They'll ask you to see what the work is when you compress it an additional distance. But sometimes it will say from your starting place at its natural length, in which case, if it had said not an additional 0.3, but from its natural length to 0.6 meters of compression, then this would be 0 if we were starting at the initial condition, but that's not where we were starting. We had that initial compression and we want to find the work for an additional compression. Okay, that's why the limits are from 0.3 to 0.6. But then once you have that set up, maybe the physics of it was a little bit confusing, a little bit convoluted. A lot of prep needed to be done here. But this integral is now very straightforward to take, right? So if we're taking the integral, this is just going to be x squared, and it's going to be 50, right? Because you're going to be dividing the 100 by 2. Let me go ahead and show all those steps so that I don't lose you guys. It's 100 times x squared over 2. And so that's going to become 50x squared. And then we can just evaluate that from 0.3 to 0.6. So we're just going to have 50. And we'll start with 0.6 squared minus 0.3 squared, like so. And then we just need to throw that in the calculator and figure it out, right? So that's just going to be what? 0.6 squared minus 0.3 squared times 50. I'm getting 13.5. And now we have to think about like what are the units here, right? So if we have a force times a distance, and the force was measured in newtons, and we're multiplying that by a distance, which is measured in meters, then this would be Newton meters. But that's what we call joules. Okay, so this is going to be joules. And that's our answer for this one. Questions, comments? How do you guys feel about that one? So it's going to take some thinking through some of these problems, but if you run into one of these spring type problems in the homework, well then you have this example to go off of. Always start by drawing a picture. You want to figure out what the function is by using Hooke's law and find that spring constant. Once we have the function, we can just use that work formula to integrate. And the integrals themselves are not too cumbersome. Okay. You guys ready for the next one or? Okay. I'm gonna let this one hang in the air for a second just to give Jasmine some time to write it because she doesn't have a copy of the notes. Um, but let's read this together. A space module weighs 15 metric tons on the Earth's surface. How much work is done in propelling the module to a height of 800 miles above the Earth? Use 4,000 miles as the radius of the Earth. Okay. So what's going to be our first step? We're going to draw a picture. Yeah. Okay. We need to know what we're looking at so that we can know what we're dealing with. So draw a picture. Okay, if you weren't an artist before, you're going to be an artist by the time you get out of Calculus 2. And if not by then, you're going to have three-dimensional objects to be drawing in Calculus 3. So look forward to that. Okay, I'm going to zoom out. Let's draw the Earth. There we go. Got a round boy there. There's my Earth. I was told that my Earth should have a radius of 4,000 miles. So my radius here is 4,000. Okay. But then we have some sort of module or some sort of space station. So here is my little, I don't know. There's my little space station just floating out here. I don't know what those are. Maybe they're solar panels, but we're floating above the Earth's surface an additional 800 miles. You guys okay with that, Earth? Okay. Well, we know on the surface of the Earth that this thing weighs, um, it weighs 15 metric tons. So there we could think of the force that was applied. F of x is equal to what is it going to be equal to? Well, let's think about Newton's law of gravitation, right? Let's bring that back in. Newton's law of gravitation is this thing F equals some gravitational constant times the two masses of the objects divided by the distance between them. So I'm just going to write that down. This is going to be G times mass 1 times mass 2 over, instead of writing this as distance squared, I'm going to put x squared. Okay, so here x is the distance. But were we given any information about the masses of these two objects? Like, do we know the mass of the Earth? Do we know the mass of the space station? Well, you would think that, but actually 15 metric tons is the force, right? So we have to remember that weight, the 15 metric tons, which is a weight, that's going to be equal to the force, right? So the reality is like, if I asked you what the mass of your body is and you stepped on a scale and you told me, oh, my mass is 200 pounds, right? Or for those of you that are skinnier than me, younger, skinnier, more agile, uh, maybe it's in the 150, 130 range. But anyway, that number on the scale, the weight in pounds, is a force. Okay, it's not the mass. So we just need to think about, like, we don't know what these masses are. I don't know what the mass of the Earth is. I don't know what the mass of the space station or the space module is. So that doesn't really matter because whatever they happen to be is going to be a constant. So think about this. Do we even need that information? Well, I know that I need G times M1 times M2 because that's my numerator. But whatever that number happens to be, it's just a constant, right? Like whatever these numbers multiplied by each other are, it's a constant, and I could figure out what that constant is. So if we wanted to simplify our lives a little bit, we could say this gravity formula that Newton gave us, and we're very appreciative of it, can be simplified to just that constant of the gravitation times the masses, c over the distance squared. So if we do know the force that was given, 15 is equal to some constant over the distance squared, well, then we can figure out what c is supposed to be. We can figure out what this constant is. Because this thing, this force that we were given, F of something is equal to 15 metric tons. That is the weight or the force that was measured on the Earth's surface, right? So that means that from the center of the Earth to the Earth's surface, that initial distance, that initial x value is 4,000. So F of 4,000 is equal to the 15 metric tons. And this x value is the distance that gave us that force. So over here, we're doing step 2 where we're trying to find that constant. In this case, we're calling it c instead of this complicated thing g times m1 times m2. We're just calling it c. Okay. So over here, we can say 15 is equal to some constant over 4,000 squared. Questions, comments before I sort of drag you guys through more of this? Okay. So maybe I'll just put here as a note that if they give you a weight is a measure of force. So make sure that you're not confusing weight with mass because they're two different measurements. Why didn't I incorporate the 800 miles? That's because we're going to use the 800 miles in our calculation of work. Okay. So if you think about like the spring initially was compressed 3.3 meters, and then we compressed it an additional zero point 0.3 meters to get us to 0.6 meters, right, of compression. So now that we kind of have our constant, well, actually, we haven't computed the constant. Let's go ahead and find what that is. So can you guys tell me how I would solve this equation to find the constant? 4,000 squared, whatever it happens to be, right? Exactly. So I'm going to do 15 times 4,000 squared, and that's going to be equal to C. And that's going to be some ungodly number, I think. 15 times 4,000 squared. It's this number, okay? So the constant is equal to 2, 4, how many zeros are there? 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7. And if you like commas in your problem, there you go. All right. But now I'm trying to answer Ryan's question. So we drew our little diagram. We solved for this constant. So now we know our function f of x is going to be equal to this number. I'm going to write it in scientific notation just because I'm lazy. So it's the same thing as 2.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 to the 8th power. That's going to be the same thing. Over x squared, right? So there's our force function. I'm gonna kind of be like kablamo. Because this is the thing that we need to integrate now. Okay. So again, if you don't like the scientific notation, you can stick with this 24 and then 7 zeros. That's perfectly fine. But here is where Ryan in the chat is asking, like, what's going to happen with the 800 miles? To find work, we need to set up our integral of this function, right? Which is f of x dx. We need to figure out what a and b are. So if the initial force that was given was a measurement here at the surface of the Earth, well, then that's going to be from 4,000, okay, actually to 4,800. But I'm having a little bit of pause here because I think what we want to do is read the problem again. It says a space module weighing this much, right, 15 metric tons, is on the surface of the Earth. How much work is done in propelling the module to a height of 800 miles? Okay. So like the final distance from the center of the Earth would be that 4,800. Are you guys okay with that? But I think that what we want to do is integrate here from our 0 point to our 4,800. Okay, because it didn't say um, an additional 800, right? Although, I mean, it kind of is a little bit confusing here. I just want to make this a little bit easier for us to think about. That integral, um, I think if we change this limit to 0, it'll be an easier thing to integrate. Okay. But in any case, we have this number, 1, 2, 3, 4, 5, 6, 7 zeros, x squared dx. Okay, so regardless of what the limits of integration are, we know what function we're integrating. Okay, so rather than trying to squeeze this all in, let's go ahead and go to the back side of this page. Work is going to be equal from 0 to 4,800 of this 2.4 times 10 to the 8th power all over x squared dx. So I'm a little bit lazy. I'm not going to write those limits of integration since we've already established what they are. How do I start? How do I need to rewrite or manipulate this equation so I can integrate it a little bit more easily? Yeah, that's exactly right. So we're going to have some constant here, 2.4 times 10 to the 8th times x to the negative 2 dx. And then since this is just a constant factor, we can go ahead and pull that out of the integral, 2.4 times 10 to the 8th, and then integrate x to the negative 2 dx. So the integration should be pretty straightforward. Should be what, negative x to the negative 1 power? Okay. Negative x to the negative 1 power. But that's the same thing as 2.4 times 10 to the 8th power times negative 1 over x. And then evaluate that from 0 to 4,800. So since plugging in 0, would this cause a problem? This would cause a problem. It would be like a singularity. So I must have messed up those limits of integration, right? We were at the surface of the Earth. Let me go ahead and back that up. Call that 4,000, because that's just not going to work, mathematically speaking. Sorry for being wishy-washy there. All right, so we're going to have 2.4 times 10 to the 8th. And then this is negative 1 over 4,800 minus negative 1 over 4,000, like so. 2.4 times 10 to the 8th. And now we can just go ahead and evaluate this in the calculator. So negative 1 over 4,800. Then a negative times a negative is going to be a positive, so that's going to be plus this other fraction, which is 1 over 4,000. We get this number, and then I just need to multiply that by 2.4 times 10 raised to the 8th power. So I'm just going to make a little note here. We're just evaluating in the calculator just because we have such ridiculous numbers here. But that comes out to something really nice. What is that, 10,000? Okay. So 10,000. Okay. Let's think about this. Our measurement in force, this is just to figure out the units, was newtons, right? Or no, it was metric tons. Metric tons. And then we integrated with respect to distance. So distance was in miles. So we can call that miles ton. I mean, we could try to figure out, what this is in terms of feet and in kilograms or something like that, so we can sort of use a conversion factor to get us back to like joules or one of these other types of measurements. But I think like, what's the point of doing that? Because it would be an equivalent measurement anyway. So I'm just going to leave it as that 10,000 since that's a really nice number. Okay. But that first limit of integration was a little bit tricky for me even this morning. Okay. And so we did need to think about this not as starting from 0 and then pushing that up to 4,800, but instead it was at the surface of the Earth first at that 4,000. and then we pushed that module into space 800 miles up. So this was our beginning limit of integration, and then this was our ending limit of integration. Okay. But the math actually worked out to be pretty nice at the end. So mistakes are going to happen from time to time. Figuring out those limits of integration, especially with these application problems, can be a little bit tricky. But that's why, like, we have to think about the homework module. We have to think about WebAssign as being an opportunity to practice, to make those mistakes. That's why you have multiple attempts on those questions, because if you make a mistake, well, then you'll figure out what that mistake was. Here, I very quickly realized my mistake because I knew that as soon as I put 1 divided by 0, that I can't divide by 0. So clearly I had like misrepresented something, right? So really nice teachable moment there. We all make mistakes, but the key is to figure out when those mistakes are happening so that we can fix them. Okay. Any questions about that problem? Feels like a lot, right? A lot of physics. Hopefully it comes into play when you guys start getting into your physics and your engineering stuff for statics and dynamics. Okay. If you like that problem, you're going to love the next one. Okay. Um, so up to this point, our treatment of work typically follows this formulation where we have delta W, right? The change in the work, or you can think of this as incremental work, is some force function times the distance increment, right? And you can think of delta X as being analogous to the dx in our integral, right? But work can also be formulated as follows, where the work, the change in the work is going to be equal to some force increment where you have a delta F times some displacement. Okay. So these are both equivalent, and the second interpretation may be useful for certain other problems, and this next example that we're going to look at is one such problem. But the second interpretation is really useful when you're looking at problems that involved non-rigid substances, things that are wigglier, like fluids or chains, right? So like if you think about if you had a coiled chain on the ground, that kind of looks like a little spiral. As you start to lift the chain or that rope up, then I'm going to put little links here. Then what's basically the weight that's being carried upwards is increasing, right? Because in that initial state, let's call it state 0, all of the weight is resting on the ground, right? It's being supported by the floor, the ground. You could think of it as the x-axis. But as you start to bring each of those links up, those links have a mass. So the more mass you have holding up in the air, the more weight is going to be forcing down because of gravity. So we're going to have a change in weight as the distance kind of grows. Does that make sense? Okay. Um, and the same is true about like pumping fluids out of tanks, right? Sometimes you have to pump water out of a tank or pump water out of a well. So this next problem, actually, we need to use this second interpretation of work, okay? And this one's a little bit more involved. So I'm going to try to, I have some notes here because I worked out this problem and I was like, okay, we really need a very pretty diagram for this. So if you're not already using pencil to write this down, definitely switch to pencil. And I'm seeing a lot of pencils, so my heart is happy. God, if I could only get my college algebra students to switch from pens to pencils, it's crazy. It's crazy the like arrogance of those students. Like I've even switched to this erasable pen for that very reason, because I know I've been making some mistakes here and there. Okay. So we have this problem. It says a spherical tank with a radius of 8 feet is half full of oil that weighs 50 pounds per cubic foot. Find the work required to pump all of the oil out through a hole at the top of the tank. So if you think about this just for a moment, we are taking a spherical tank and we're pumping the oil that's in that tank upwards. That means that we're going to be thinking about distance in terms of y values, which means our function needs to be in terms of y values. Okay. So let's go ahead and draw a picture so that we can make sense of this. So let's draw a picture as our first step. And I'm going to set this up very neatly with an x-axis down here and a y-axis here. And this circular tank, I'm going to put the bottom of the circle, or the spherical tank rather, I'm going to put the bottom of the sphere on the origin of my coordinate system here. Okay. I'm going to zoom in so we can see this picture a little bit better. So if the radius of this sphere is 8 feet, how tall is the sphere? 16, right? So we have a 16-foot tall sphere. And there's a hole at the top of our sphere where we're going to be pumping this oil out of. Okay. Now, if you're not a fan of sort of 3D images, I am sorry, but I'm going to draw this as a sphere now because it has some dimensionality to it. It has some depth, right? So we know that the radius here is 8 feet, and that's how we were able to figure out the height of the sphere. Okay. It also says that this thing is halfway full of oil, so that's why I drew this little inner circle here to represent we have oil all in this area, but I'm not going to shade it in because we might need to draw some more stuff. Okay. I hope I didn't lead you guys astray as soon as I started doing those shading marks. Okay. And let's think about what they gave to us here. They said that, well, we need to be pumping this in the upwards direction, right? So what I really want to do is think about like the differential of work is equal to some incremental force times some distance times, yeah, some distance, right? That's the key that we need to think about, right? But for now, we need to think about what is this force, right? What is this incremental force? Okay. Well, the incremental force is going to be equal to this thing that they gave us, which was 50 pounds per cubic feet, right? Per cubic foot. But this technically isn't a force measurement. This 50 pounds per cubic foot, that's kind of a measurement of density, right? Because you have a force divided by a volume, right? So what we need to know is to get the actual force, we need to get a volume here to multiply, right? So that we can cancel out the feet squared. So maybe I'll put volume in feet, sorry, feet cubed, right? Because we want those units to cancel out so that we just have a force. Okay. So when we say the increment of force, we're not going to think about the entire force that this halfway filled amount of oil is going to exert downward. What we're going to do is make this a little bit easier and sort of cut out like a disc, right? So think of like we have a layer, a little disc of oil, like resting on top, right? This disk has some thickness. We might call that delta Y, right? The volume for that disk of the disk. Well, if we have this disk, what is this shape? I mean, would it be helpful if I elongated it like that? Right, I'm sort of exaggerating the delta Y, right? The thickness of the disk. But what is this general shape? Yeah, it's a little cylinder, right? So if I just need a geometric formula for the volume of the cylinder, that's going to be the area of the circular face times the height of the cylinder. So if we think about the area of the circular face, going back to our original image here, the area of a circle is just going to be pi r uh, squared, and then times the height of the cylinder, right? So that means that we'll have pi, and then our radius for these little disks, that depends on where we are on the function, right? Or where we are in sort of like the this semi or like this half sphere on the lower side of the spherical tank. Like here in the center, we have a radius of 8, right? So we know that that x value is equal to 8 there. But if we were like pumping some of this fluid up, eventually you'll reach sort of these lower parts of the tank, which would have some other radius. I'm going to call this x1, right? So depending on where you are in terms of pumping that oil out of the tank, the x value is going to change, right? Which means that that radius is going to change. So this is really x squared, right? Because the radius is represented by the x value. And then we're saying that the thickness or the height of these little cylinders is delta y, right? So if we go back over here with this information, the incremental force that we were trying to come up with is going to be the 50 pounds per cubic foot times pi times x squared times delta y. However, if we try to integrate this, right, like we had this thing times distance, well, because our we're pumping the oil upwards, this distance is going to be in terms of y, right? And that means we're going to be integrating with respect to y. So we shouldn't have a function that has both a delta y in it and a delta and an x in it. We want to make sure that this equation is in terms of y only. Okay. So here's where it gets a little bit more dicey. Okay. I'm gonna sort of partition this a little bit. We want delta F to be in terms of y only, meaning we want to sub out the x squared term. Okay. So let's go back to like our little diagram here and think about like just this face of our sphere, right? If we're thinking about this face of our sphere, we have this circle, right? It has a center in terms of our y values. if this sphere is 16 feet, then this is 8 feet up from the bottom of the sphere, and then 16 feet up to the very top of the sphere. So like the center of our circle is at 0, 8 with a radius of 8. Do you guys happen to remember what the equation of a circle is? Again, this is kind of drawing back to some algebra or pre-cal stuff. And no is an acceptable answer if you don't remember. So if we had like a circle that was centered at the origin, the equation of the circle would be x squared plus y squared equals the radius squared. Do you guys remember ever seeing that? Okay. But our circle is centered at 0, 8. So the y value is at 8. So what we would need to do to modify this equation is the x squared would be fine, plus then we put y minus 8 squared so that the center now goes up 8 units. And then we know that the radius is 8. And then we square that. So this is going to be the equation that represents the circle that we're dealing with. Okay. And now through some algebra, we need to simplify this a little bit. Okay. So I'm going to call this x squared plus this guy. I'm going to put in brackets just because you need to sort of write this out twice and then square it. But you'll get y squared minus 16y plus 64. Okay, I'm going to zoom in here. Equals 8 squared is 64, so I'm going to put that 64 down. And now I just had like a split second of emotional anxiety. So I'm going to say, is 8 squared 64? Okay, now I've checked it on my calculator because I also sometimes freak out. Okay. So now we just need to get this in terms of y only, right? Basically, we're trying to solve and get the x squared by itself. So if I moved all of these guys over to the other side, I would have to subtract y squared, I'd have to add 16y, and I'd have to subtract 64, right, from both sides. So what I'm going to end up with is x squared is equal to, we're going to have a positive, I'm just going to put negative y squared because that's moving over to the other side. Then we'll have a positive 16y. And then when we have 64 minus this 64, those are going to cancel out. Okay. So x squared is equal to this expression here. And this thing is what we can substitute back into our force equation that we're getting here for x squared, right? Because now we can basically make that substitution and we'll have a force equation that's in terms of y only. Okay? Are there any questions, comments? It feels like it's pulling in a lot of older knowledge, right? Okay. It is what it is. That's the nature of the beast. But that's why we're continuing on to the next page. Okay. So let's get our bearings about us and think about what it is we're trying to do here. We're trying to get our change in work, which is equal to this delta F times some distance. Okay. And now we have that delta F is going to be equal to 50 pi times, and instead of x squared, we're going to substitute that with the negative y squared plus the 16y minus y squared plus the 16y delta y. Okay, so that is this part here. But now we need to think about how can we formulate the distance that's going to be traveled as we pump this oil out of that circular tank. So I'm going to go back to my picture and say, if we are like right here at the very top surface level of the oil, since the sphere is filled up halfway. Then you could say like, oh, I need to traverse a distance of 8, right? But we need to think about all of the different layers. So like if I chose a layer of oil here, somewhere at the bottom, then this distance is represented by y. And the remaining distance from some given y value that needs to be traveled is going to be the 16 minus y. So this guy is actually going to be the distance traveled by any given layer of oil, depending on which y value it's at, right? So that distance is going to be given by the 16 minus y. Okay. And now we can have delta work needs to be simplified, right? Just to make the integration a little bit easier for us. I'm going to rearrange this to 50 pi in the front, and then I'm going to put the negative y squared plus the 16y here. I'm going to bring this other parentheses, the 16 minus y, and then I'm going to throw the delta y in the back because when we integrate that, that delta y is going to be a dy, right? So we always like to have that sort of in the back of the expression. This full thing now is what our delta work is, but we need to FOIL this guy out with this guy out, okay? So I am already sick and tired of this problem. I'm just gonna make um, a little grid here so that I don't make any mistakes. Because when I say I'm sick and tired of this problem, I mean like I'm starting to get fatigued. It's been a long journey, and I'm starting to sort of thinking I'm gonna make a mistake somewhere. So I'm just making my little grid to FOIL this out so I don't make any mistakes. So this is gonna be negative 16y squared. 16 times 16 is going to be some god-awful number, right? 16 times 16 is going to be 256y there. Then we have a negative and a negative, so that's going to be a positive y to the third power. And then this will be a negative 16y squared also. So when we FOIL that out, we're going to get 50 pi times y to the third power minus 32y squared plus 256y times delta y. And now we just need to integrate this, okay? So how do we need to integrate this? So we're going to say that work is equal to the integral, and we're going to figure out what our limits are by going back to our diagram. So I'm going to hold off on that. 50 pi times y to the third minus 32y squared plus 256y dy. Okay. And if you want, you know that you can pull out the 50 pi outside of the integral and make this a lot easier. But going back to our diagram here, and I know that at this point it's very, very busy. Okay. So if we're trying to say that like this spherical tank of oil is filled up halfway, then the place that we're starting at is a y value of 8. And to pump that stuff out, at least to the hole that we're trying to reach at the top, that's going to take us to a height of 16. Are you guys okay with that? So we're going from 8 to 16, integrating this god-awful function, right? I'm going to pull the 50 pi out of the integral, going from 8 to 16. y cubed minus 32y squared plus 256y dy. And then the integration is not too bad, right? It's the algebra that's really killing us here. So we got to have that stamina for the algebra, but this integration should now be what? 1/4 y to the fourth power minus 32 over 3 y to the third power plus y to the second power. And I'm just going to divide the 256 by 2 since that's going to be the denominator. That's going to be 128 now. And then we'll integrate that from 8 to 16. So to make this a little bit easier, and you probably noticed that I did this on one of the earlier problems today, one of the easier problems. Because we factored out the 50 pi, I don't have to put 50 pi and then plug in the 16 and then minus the 50 pi again. I'm just going to integrate this stuff that I have in the brackets. And since both of them would have a factor of 50 pi, I can just multiply that 50 pi at the end. Okay. So in reality, I'm going to take 1/4 times 16 to the fourth minus 32 thirds times 16 to the third plus 128 times 16 squared minus, I'm going to use braces here for my lower limit, 1/4 times 8 to the fourth minus 32 thirds times 8 to the third plus 128 times 8 squared. Okay. So I'm just going to do all this stuff on the inside of the brackets here, and then I'll just multiply by the 50 pi at the end. So now we get to typing. 1/4 times 16 raised to the fourth minus 32 thirds times 16 raised to the third plus 256 times 16 squared. Yeah, that's right. Thank you for catching that. 128, because I divided it by 2, right? Okay. I wonder, oh God, I hate these numbers. Okay, I'm gonna do 50 pi, and then this first number is 5,461.333 repeating, right? And a third minus, let's go ahead and plug this in now, but now I'm just gonna swap out the 16s with 8s. Just make my life a little bit easier. And all my coefficients should still be good. 128 times 8 squared, good. That's going to be this. 3754.666 repeating. So it's this number minus this number times 50 pi. And I'm getting approximately 268082, which is 268,082.573. Okay, I hate to squeeze this in, but that's going to be the approximate value for force. And the force distance, I don't even remember what our units are. Let's go back to our drawing here, back to the original problem. It was pounds per cubic foot. So when we found the force, we canceled out the cubic feet, and so it was just pounds. So in terms of our force, that was pounds. And in terms of our distance, that was feet. So that's going to be foot pounds. Okay. Was that god awful, guys? Hell yeah. right? So some of these problems are going to be very, very, very tricky. You're going to need to give yourself the time and the grace to sort of get through those. And I know that we're ending a little bit early, but I think that we're all exhausted from those, what, 3 or 4 problems that we did here. So we'll call it a day.